Next week, we've got River coming to give us a talk about simulating a small universe. So that'll be fun. It's based on a recent title by Wolfram Alpha, so check that out. I want to thank our lovely sponsors who make all this good food possible. Thank you, sponsors. Round of applause for the sponsors. Yep. If your company is looking to sponsor Chattanooga, we are registered 501c3. Sweetening deal there for you. Without further ado, everybody give a warm welcome to Wil Wade.
I'm Wil Wade. I'm one of the developers here in the building at CarbonFive, just a few floors above us. And today we're going to talk a little bit about a fun thing called a Clojure. So Clojure is a language, and we're going to do a Clojure speedrun. So this is inspired by, you might have seen the learn X in Y minutes or something like that. So the idea at the end of this is that you're going to be able to walk away and you're going to be able to read some Clojure, you're going to be able to write some Clojure if you want, and you're going to have just a general early familiarity with it, all smashed down into this, hopefully, 50-minute talk. We'll see how we get through it. So a couple of things you might be wondering, why on earth should I learn another language? How many people know more than one language? Most everybody. Okay. Why would you want to learn another one? No ideas. All righty. We'll do this the hard way. One of the best ways I like to learn new languages, one of the main reasons I like to learn new languages is that each language tends to have its own ideas about what's important. And when you learn, you kind of learn different things from different languages. So if you're wanting to learn today about some fun stuff called Lisp and immutability and composability, then this is a great talk for you. And we're going to get started right away. So first off, how do you get Clojure set up? Go look at clojure.org and Google. It's like step one. You guys can handle all that. So we're going to skip past that. And what we've already got here running is a Clojure REPL. That's a read, evaluate, print, and loop, which allows us to evaluate Clojure statements. And we'll be in this for most of the talk. And this is kind of step one for most of your functional type languages if you haven't done one previously. And so the first thing we're going to do in this talk is we're going to talk about addition. That's kind of the first thing you always want to do in a language. So let's go over here and let's type our 1 plus 1, and let's see what we get. Oh, we get 1. 1 plus 1 equals 1, so that's great. We're starting off on a great thing. So Clojure is of a family of languages called Lisp, which work more on a list. So instead of having an infix notation, where the plus is in between the two values, we have our function, and then we have our parameters for it. So if you're used to doing something like maybe add parentheses 1 comma 1, then this maybe feels a bit more like that. So we've got our function call at the front, and we've got a list of things, and we can do all kinds of addition that we want to do. It also evaluates through the when it needs to. So we have a function inside of a function. So if we need to call that 3 plus 7, it's going to actually take that 5 plus 2, evaluate it, and then make the other addition. But if you don't know, Lisp is a language that's been around for next year's, I think, the 60th anniversary of Lisp, give or take a little bit. So it's been around a long time, and it's based on this concept of list processing. So most functions, most of your built-in functions and a lot of the functions that you may be writing actually take a list. So you can actually give it 3 values. So how's that? You have a plus, that normally a binary operation that can actually take 3. And in fact, it can take as many as you want. So you can actually give this thing lots of different things. And that's how, again, a lot of these work. They're able to take any number of parameters. And we can do all our other mathematical operations. And we can even do things like, this is a fun one, equals. So you want to know that more than one thing is equal. It doesn't just have to be 2 things. You can have a whole list of things. And as long as they're equal, or in the case where they're not equal, that all works out quite nicely. And we've got greater than, less than. And you see here that The order, of course, matters for greater than and less than, and it will nicely fail on us if we have something that is not, in this case, strictly greater than in our list. So there are two different types of lists in Clojure that you can actually build up. And we're going to talk about the two main ones. We have lists. So here we are, we're building up a list of 1, 2, 3, 4, 5. And so this is just defining it with the function list, and then it returns us back our list. There's also a quote syntax, which can be a little bit tricky and we aren't going to get into, but it's a lot of fun. But for the most part, unless you're putting in an actual expression inside the quoted form, these two are actually equal. There's no difference between them unless you have an expression inside the quoted form, in which case it gets a little hairy and a bit past this talk. We also have vectors. Vectors are a little different than lists. Lists are actually actual linked lists. So it means it's easy to get that head, and it's easy to add to the head of the list, but it's not easy to get the nth value of the list. A vector is actually an array form underneath. So getting the nth value of a vector is just as easy as getting the first or last value of the vector. And we again have a short syntax for the vector of just square brackets. And you'll see a lot of these when you're actually building up any kind of actual list that you're going to enumerate. And again, those of course are, there's no difference between these two in this case, unlike the quote syntax, which is a little strange at times. So let's get into some variables. You know, we've gotten some mathematics now, we've got some lists, we can get into some variables. And in Clojure, we have this concept of a let block. So these variables are scoped inside of this parentheses block around the let, and we have a vector after the let, which gives us a variable that we're going to bind to, a symbol that we're going to bind to, and the actual value we're going to bind to it. And that allows us to do some nice little stuff. It also allows us to actually build these things. So once we've defined it on the first level, we can give it expressions, and we can use our variables that we've already defined up the tree. Go for it. They don't mean anything. That's right. In Clojure, there's only one type of white space, and that's everything that's white space and commas. So if you really like your commas, you can write your Clojure with commas. Please don't do it in any of my repos, though. If you're working with variables, though, one of the key tenets of Clojure is that your data is immutable. So you're never mutating a variable. That means that any kind of method that you're calling on a variable, like maybe you call the increment method. So here we are, we're printing out the variable a, and then we're going to print out the incremented variable a, which is 6, and then we're going to print out the incremented variable a, which is 6 again. In a mutated variable, this would actually then be 7, but then we're going to decrement a, which is still a5, and we get a 4, and then if we print out a again, we find it's still our original value. Nothing is actually changed about this value. So in Clojure, anytime you give a variable to a function, you're going to get back a new variable. You're never going to change that thing. However, watch out, you can reassign a symbol. A variable is just a symbol. You can reassign. This is generally bad practice, but it's something to watch out for as you're working through stuff. So I think we're done with numbers for now. We've had a lot of numbers already. So let's move on to another fun piece of Clojure, which is keywords. And you find this in a couple other languages, but you can actually have words that are symbols. So in this case, you can create a keyword using our keyword function, or again, the short syntax of a colon, and this actually returns back nothing but itself. So if we ask for test, it returns itself, and it always will return itself, always resolves to itself, and it allows us to do some fun things, like we can put it into a list and we can ask for the first thing in that list and it's just going to give itself. We can ask for the last, maybe a random one if we want. And it becomes really helpful when it comes to hash maps. Clojure has a couple different types of maps. We aren't going to get into all the different types today, including it has a really nice set. If you're used to working with sets, it does indeed have that. Works great. But here is our standard map syntax. So we have keys, and then we have values. And you can associate new values to it. Again, you can see how we got this list of things. We're not just associating one thing. We're associating pairs of things with it, including, in this case, we actually have a string there. The D value is keys don't have to be keywords. They could be strings. And we can disassociate things with it. Standard kind of mappy things. But we can also do fun things like this. We can use a map as a function and then ask it for its A value. Or we can even do that with strings. So if you wanted to get the value out, that's pretty nice. We can also actually turn that around for keywords, not for strings, but for keywords, and use keywords as a function to pull things out. This is really useful if you're mapping over things, trying to pull data out and work with it. We also have that you can pull out a value that isn't there, and that value is always going to be nil. In Clojure, it's very important to remember, as in with any new language, what truth is. What is false and what is true? In Clojure, nil is a false value. So here's a basic if statement. So if nil, return the string true. If false, then we're going to return the string false, and it is indeed false. And we see that we only have two values in Clojure that are falsy, and that is nil and false itself. Nothing else, maybe you've worked with something where like an empty vector or an empty array is falsy. It's not. An empty string, it's not. 0, it's not. Two values are falsy, and that's it. So we're going to get on one last little fun piece of syntax that you're going to find if you're looking at a lot of Clojure code or if you're doing a lot of regular expressions, because they're great, if you can remember what the symbols all mean. And so here is just the basic syntax for a regular expression. We got a hash, and then .l plus, so we're getting all the L's, and that's returning us a nice little sequence of all the value and then where it has one or more L's. This is an important place to stop and think for a second about Clojure and what Clojure actually is. So Clojure isn't something that actually runs. Clojure compiles, and it compiles, in this case, it's actually compiling to Java underneath. So you can actually take your Clojure code, compile it, you're going to end up with a jar file at the end, and you can ship that jar file just like you'd ship any other jar file you would like. Clojure, however, doesn't have to be based on Java. It can, in fact, compile, if you're using Clojure script, it compiles directly to JavaScript. And there's some fun stuff in there. And it can also compile to a few others, but Clojure script and Clojure on the JVM are the two most common. Everything you see today can actually compile both in Clojure and Clojure script. So this whole thing we're running right now on the JVM, it could all run straight in JavaScript on the browser once it compiles. But there are a few catches. And some of those catches are things like with regular expressions. Java regular expressions are ever so slightly different from JavaScript regular expressions. Rarely do those changes matter, but if you're writing a regular expression here, this is not a Clojure regular expression. Clojure regular expressions are merely a pass-through to the underlying level, and so we're actually building up here a Java regular expression, and this is just syntax on top of that. So if this was compiling to JavaScript, though, we would have a JavaScript regular expression. And if you had one of those strange little things that are different between the two of them, because everybody has to be special in their own way when it comes to regular expressions, this is something to watch out for. So it's time now to move on to finally, we're there, we've got it, we're going to functions. Okay, so we've got all our basic data types. There's a few more, but you got most of it. You got enough that you can probably get your way through. So let's start building up a function. So here we go. We're going to define a function. We're going back to mathematics because that's what I get on my degree. The standard setup here is that we have define a function, and we got our name of our function, and then we have an array. We have a vector of our parameters, and then we have the expression or expressions that we're going to evaluate. In Clojure, like in a few other functional languages, you don't have a return statement. There is no early returning. You merely return the final expression. So in this case, we can actually define these inside the REPL and then turn around and use them, and it's going to return that value of that expression. In this case, we're just really aliasing the addition. We can also find that it doesn't work exactly like the add function does, unfortunately. We can't take any number of arguments. So there's a fun way in Clojure that actually lets you take a function that only takes a binary operation to a list. That's our reduce function. We'll talk some more about this in a minute. But if you're used to using reduces, there we go. We've got a reduce in there, and we can do that. But I think we want to kind of emulate that same concept of being able to take any number and add them together. So let's take a second and remember what a reducer actually does. So what we're actually doing here is we're taking a list of 1, 2, 3, 4, 5, and we're going to apply our addition function in this case to each pair in turn. So we're going to go from 1 plus 2, that turns into a 3. That's our 3. We're going to add 3 to it. 6, add the 4 to it, and we're reducing all the way down to that 15. So here we can actually build up that same thing using our reduce function, and we're using this nice little syntax, this ampersand syntax up there. That'll take all of the variables given to our sum function and put them into a vector for us. So then we have that vector, just like we had a little bit ago, and we can indeed see that our sum function can nicely take any number of variables. Another fun thing that we can actually do is destructuring. So if you've written any of the newer ECMAScript, you might have gotten a chance to play around with this. And so we can actually take a map, in this case, as a variable, and then break it apart into different variables that we're actually going to use inside of our function. So in this case, the one big difference between like an ECMAScript is that the syntax is we have the variable that we're going to map it to first, and then we have our key. So in this case, we're taking the string key of A. Whatever we give it, we're going to map it into val A. And our keyword key of colon B and map that into our B syntax. So here's our map. We're going to add this map. And it's going to take that and actually add the 1 and the 2, and it's going to ignore all the other values that's given to it. That's really important because in Clojure, it's not a strongly typed language. It's a bit fuzzy typed, and the nice thing, though, is that we can build functions that take maps, and it doesn't matter what that map is, it merely matters what data is in the map. And so it can take that map, and you can say, let's say this was a maps of 2 different records in the database, right? We can take that, and it's agnostic to what the actual data is. All it cares about is that it's actually getting the values, in this case, a string key of A and a keyword key of colon B, and then putting that together into this method. Yeah, it's missing my quote marks around it. Yep, that's just I missed this one when I was fixing all those being printed out properly. Commas are just the white space, right? It's just a nice way to visualize that. So another destructuring you can do is you can destructure your vectors. And so this is a lot simpler. You're just taking the first value and the second value and adding them together. And here we go. We can take that, and we see that it pulls out the 4 and the 2 and adds just those together, but it ignores the 87. Yet another fun thing we can do is we can do multi-methods or multiple arity functions. So we're going to define one function here, add me, which can take 1 parameter, or it can take 2 parameters, or it can take 3. You can also build up other versions of this. And so in the case of 1, it's going to take the value and just add 100 to it. There we go. So it's 101 is the outcome there. And then that second one, we're going to actually call itself with another arity. So we're actually saying, if you give me 2, we're going to add the 1 and the 2 and the 3 there, and it's going to pass that over to our final version, our 3-arity version, which will just add those 3 values. So 1 plus 2 plus the 3 equals 6. And then finally, the 3-arity version is just going to take the 3 and add those together. But not always do you want a fully defined function. So we have nice lambdas, we have anonymous functions, and we have a couple ways to do that. But remember, in Clojure, functions, in this case the increment function, is something we can pass around. They're first-class citizens of our language. So we can actually take any function we've defined and pass it along without evaluating it, which is why it doesn't have our wonderful parentheses around the increment. And it can then later evaluate that down the line. But we can also do things in a nice short syntax. This is great for little short things using a hash function here. And that's just building up a quick little anonymous function. And then any parameters that come in are %1, %2, %3, and so forth. So you can build up nice little short things. We also have another one, should you like it. This one actually has specified and named. And we can also name the actual function, the anonymous function itself. This you aren't going to find very much, but if you're worried about your stack traces or something like that and you really want it to be nicely named, you're going to do that. And again, see how that's that last expression, in this case only 1, but it's that last expression that's actually being returned. And so here we're mapping over 1, 2, 3, and adding 4 to each one. And get this, you can also destructure inside of your anonymous functions as long as you use the function syntax. So you can actually, in this case, destructure using the vector destructuring, but you also get access to all the other kinds of destructuring you could want, which can be very, very useful. So we've seen map and we've seen reduce. And I know that sometimes if you're new to functional languages, map and reduce can be a bit confusing as to which one should I use when and how do I use it. So the easy rule of thumb is map is going to consume a list and it's going to perform a transformation on each item in the list. While reduce is going to take a list, it's going to perform a transformation on each item in the list while having access to everything that has been transformed previously. So that means, in effect, we can actually take and reproduce a map function using the reduce function. So this is a fun little way to look at it. So we're building up this is a simplified map function, I should say. And so the values you're getting here are not going to necessarily always be exactly the same as if you're working with the actual map function. This is most simplified. Don't write your own map function. Use the one built in. But this is a great way to look at the differences between them. So we've got our function coming in here. That's our f. And then we have our array of values, our vector of values, which is often shown as x's, the plural of an x value. And we're going to just pass it straight to our reduce. And let's look at it from bottom up. So here's our vector coming in. Here's our initial value for what we'll call the accumulator. And then here is our anonymous function that's going to be applied. And this is a conjoining. And so we're actually going to take, the conjoin is going to take this value, this vector, and append this value to that vector. So we're going to take, let's say we're going to reduce over a list of something like 1, 2, 3, which we can see there. It actually works the same. My map works the same as map. So we have an increment function, and we have 1, 2, 3. So let's take a look and see what's actually happening in here. We know this is increment, and we have 1, 2, and 3 here. So the first time this runs, we're going to have conjoin an empty vector to increment 1. And so it's going to evaluate increment 1, which gives us 2, and append it to our empty vector, which gives us a vector holding the value 2. Then we're going to take our next one. Our next value out of our original vector is 2. So we're going to pass that into here, increment it, gets the 3, and then it's going to conjoin it with a vector that, in this case, already has a 2 in it. So now we have a vector of 2 conjoining to the the 3, and so forth. So that's the kind of the nice little difference between those two. We have, besides just functions, you can also just define something. Often place you're going to find things defined is maybe with a config statement. So here's a config map. We have our Twilio key and our Twilio account. Not a real one. It won't work if you're trying to send text messages. And we have some other config. Is something enabled? Maybe, maybe not. And you can actually then turn around and use that config and give it things. Remember, it's just a map. And we can say, hey, is something enabled? Or we can say, hey, get in the config, get the Twilio key out for us. And maybe sometimes it doesn't actually have an endpoint, so we just want to use that default value there. So defing can be very useful, and we'll use it when it comes to dice time. So we're going to actually, this is our first little time to play around with some of this fun Clojure stuff, and we're going to build some dice. So here's a simple D6. So that's a nice 6-sided die. And it's a def because this is not going to change. You can't pass this anything to change it. So it's going to be the same thing. And we're just going to take a range of 6, which is 0 through 5, increment it 1 because there's no 0 on a standard D6, and then return that. And so there it is. We got 1, 2, 3, 4, 5, 6. It's pretty nice. But at this time, it's time to start really thinking in terms of Clojure. And so we need to talk about macros. So Clojure, we already said it's a compiled language. It compiles into Java. But there are actually two different types of things in Clojure. There are things that happen at runtime, which is everything we've seen pretty much so far, with a few exceptions. But for the most part, everything we've seen runs at runtime. We also have things that happen at compile time. And so it allows us to do things like this. So this is our double arrow threading macro. And it is merely taking the first value, passing it into the last place of the second one, and then taking that value and passing it into the last place right there. And it performs that transformation when it's being compiled. It makes for some nice, easy ways to write things that indeed work exactly the same way. So here it is again. We see there's no difference between passing the 6 into the range function and then it being called and just calling the range with a 6. Now, obviously, you wouldn't necessarily use a threading macro just to pass one value in, but we'll see it again and again over the next few times. Some people don't. Some people do. But you can see here it starts to make a little bit more sense as you start building up this list of transformations that these values are going to go through. So we're transforming a 6 into a range, and then we're going to take 2 values off of that range. So numbers just on dice. There's more dice out there than just a D6. So let's build up an NED. So we can actually use that. Then here's a D20. And we can also then turn around and let's roll that d20. And here's an any roll. You can roll any numbered sided die, and it's just going to take a random value out of that list. And so we can roll a 20. No natural 20s for us today. But we could have just used a random function. Like, there's no real reason for that. So let's look at custom dice. Maybe you're making a game or you're making maybe a solar system. So here we go. We have a list, in this case a D6, that builds you up a solar system die. So let's have something that'll roll that space die for us. There's a little function, just takes the random nth out of it, and we can roll it. We'll get a star. There's a dwarf planet. Sorry, Pluto. And here we get to yet another fun piece of Clojure. Clojure believes that laziness is a virtue. I believe it too most of the time. My wife, not so much. But so here we can do something. We're actually repeatedly is a fun little function that actually will repeatedly call roll space die. And it will do it, and it creates a list of infinite length. We can take 3 off of this list. We can take 5 off of this list. We can take as much as we have memory to take, but it's not actually going to try to do that until later, which allows us to do things like this. So map a name. Name takes a keyword. Remember, we were working with those colon keywords before. Takes a keyword and just turns it into a string for us. And so we can actually repeatedly roll the space dice and map it to a name, but then it's not until we say take 5 that that actually gets evaluated. And you see here again we're using that nice arrow, double arrow macro, and here's even, we can make it a little bit nicer, right? So we take our space die. We have a function that just returns the space die for us, because it's deft just to that one value. And then we're going to repeatedly call that. So we have a list, an infinite list full of space dice. And you thought you were coming to a dev talk that wasn't going to be interested. I just said we have an infinite list of space dice. I mean, that's just awesome. And then we're going to say, take a random one out of each space dice, turn that keyword into a name, and then we're going to apply a nice little capitalized function to it. And then we're going to take 5. And so we have our dwarf planet, our gas giant, and so forth. So now with that wonderfully exciting piece, we're going to talk about what we are actually kind of doing with that, and that is transducers. So transducers are a wee bit strange if you haven't worked with them too much before, but they're nice and easy because we have worked with them before. So here's a rand inth. This actually is a transducer. It's going to take, this is a function that it returns a function that you can put into something that will then take the random inth. We have take 5. That's also one. Filtering to our stars. That's also it. And we can take these transducers and we can compose them to build a new transducer. And you're like, all this transducer stuff, what can I actually do with transducers? Well, you can pass them to things like sequence. Sequence is actually going to take, it can actually take a lazy sequence. In this case, I just gave it 3 space dice. And we can say roll for string, and that's going to apply this composed function for us. We've got things like into, so we can take roll for string, and we're going to actually push it into, in this case, a vector, or here's a fun one, actually transduce it. So this is actually going to take our list, apply that set of functions to it, and then in order to accumulate it into a single value, we're going to apply our string function, which gives us a nice little, lots of dwarf planets. So we get, now you're at a point where we can now actually start looking at an actual application. So let's first start off by, what are we going to do? We're going to play blackjack, right? Blackjack's a nice simple thing to play. And the nice thing is this blackjack is not entirely complete. So all this code that you've seen is on a repo that you can get to, and you can go and add your favorite part of Blackjack to it. But let's actually look at this. So first off, we have our namespace declaration. So that gives us some level of control over how our functions are and where they are in different files. And so we're going to look at, here's an actual card. So remember, it's a multifunction, and it's a multifunction that's calling itself. In this case, it's saying, hey, to build up a card map, this is going to be our representation of a playing card. We need a value for that card for Blackjack. We need the name of the card, and we want the suit of the card, of course. The suite. Suit. Yes. So, and here you can see how we're actually saying, in this case, for the name of the card, for ones that just have 2, we're going to just pass in a string version of our value. That's for our 2s, 2 through 10s. And so here we go. We're going to generate a suite of cards. And we're taking, again, there's that arrow function. So we're taking a range of 2 to 11. Remember, a range is not going to include that final value. So this is 2 through 10. And we're going to map that across our card function. So in this case, we're actually passing in that string. We wouldn't have to, thanks to our multifunction. And we're passing in whatever our suit is, which is coming in here. And then we're going to concatenate that list with some special ones here, which are, of course, our ace, our jack, and our king. And so here we go. We're going to actually then take those, composing all these functions together to build up a deck of cards. We have hearts, clubs, spades, diamonds. And we're going to map these 4 against our suits of cards. And we're going to apply the 4. We get an array back with 4 arrays in it. And apply is going to take an array, take all the values out of the array, and apply it to, in this case, our function concatenate. So it's going to basically do a quick flat map for us on those few. So there we go. Nothing else. This doesn't call anything outside of itself. It's nicely self-contained. And we can turn around and use that on things like maybe a turn. So here's a fun little function. You have to figure out how much, in Blackjack, you need to figure out how much the hand is worth, right? So we have, we're getting in a vector of cards, because that's a hand, is a vector of cards. And we're going to pull out all the values. We're going to map across the values of the cards. And we're going to apply an addition function to the values. So maybe we have 2 cards, 10 and a 5. So we have the cards come in, we get the 2 and the 5 out. We're applying the plus to the 2 and the 5. And we also have this little ace count, because aces, of course, if you're not familiar with Blackjack, aces can be a 1 or they can be an 11. They give you some flexibility in that. So we're actually going to filter all of our values to find out which ones equal 1. And we're going to give a count of that, and that tells us how many aces we're holding in our hand. Nothing here, of course, kicks you out if you have more than 4 aces. But, and then we actually handle that ace. So this is a conditional. So we have a conditional here that says, hey, if we have 0 ace counts, if we don't have any aces, we don't have to deal with anything, just return back the sum. If our sum is less than 11, then we already know at this point we have an ace. And so you only ever want 1 ace to be worth 11, so we're going to add 10 to that sum. Or, in that case, if we have maybe 12, you have an ace, but you're not going to want it to go up. The else here, remember, everything besides null and false is truthy. So else is a nice little way to say otherwise, even though this value could be any truthy value. It's a nice little keyword to say otherwise, we're just going to finally return the sum. Now, of course, if you're working on your stuff, you want to write a nice little test. So here are some simple little tests. We see a little bit more of the namespace declaration stuff where we can require different pieces and parts and refer some of those functions if we want to refer them. And we can see here we have a nice little, we're going to sum the hand. So we're testing that the hand, in this case, should sum to 12. We're giving ourselves 2 cards. We're generating those cards on the fly as we need to. And we're just checking that the sum of those 2 cards is indeed 12. And we're asserting that something is truthy. And we can look at here, aces should go to 11, because everything should go to 11. And we have our ace, we have 2 other values, and we see that it is indeed running to 11. We see here that aces, in this case, should stay at 1, because otherwise you're going to go over your 21. One final thing before we get to play this game is that blackjack has some state in it, right? Nothing we've talked about so far has any state, but blackjack has a state. You have cards in your hand, and those cards change. So, and we also have a deck, and that deck gets shorter as we go through the deck. And so here are a wonderful little invention that the creators of Clojure have given us, which is the atom. So an atom is actually a thread-safe piece of state. And we can set that state. So here we're going to create a deck. So we didn't actually look at that deck. We looked a little bit at that deck. We're going to shuffle up that deck, and we're going to apply it to an atom that we're going to define to be the deck. We're going to start off. Here's our initial player hands. We have a dealer and a player. That's it. And we have a turn counter because we want to know how many turns have gone by. And then here's a little quick way to say, hey, when you start a new round, we want to reset the turn counter to 0, and we want to reset our hands. And we also, if you want to restart the game altogether, you need to make sure that you shuffle that deck as well as starting a new round. And then here, if you want to actually take a card, right? So you're actually saying, we're taking the first off of at the deck. So the at, when dealing with an atom, dereferences that atom. So it takes it from just being an atom to actually the real thing that we're going to take the first value off of. And then we're going to perform a swap function on the deck, which allows us to basically say, swap says, hey, this atom here, perform this function, which in this case is rest. Or if you're used to it, more of the tail. So this is the rest of the list outside of the first one. Cuts off the first one. So that actually takes our deck atom and updates our state to say, hey, that first one, we've drawn it, forget about it. So there's a little bit more, but here you can actually see this is actually, taking our first turn. Here we're actually destructuring inside of a let statement. All kinds of fun things to kind of go through. There's that dereferencing again. But let's actually, let's play this game, right? So this is our little, we can actually play this in the REPL. And so we have here's our little interface to play this game for now. This could easily be mapped up to whatever you wanted, say an API or at the console, or maybe even, because again, everything you've seen can compile to JavaScript. You can just set this up in JavaScript however you want. So let's look at taking a turn. So here we are back in our REPL. We've loaded up our Speedrun core namespace. And let's cross our fingers because that's important for live demos. And so here we go. This is turn number 1. Our hand is a 5 of diamonds, 10 of diamonds, and a 5 of spades. So should we take a hit?
Yes.
Yes. Okay. Let's take a hit. All right, we take a hit. The dealer took a hit. This is turn number 2. Our hand is a 6 of clubs, 10 of diamonds, and a 5 of spades. We now have 21. Good job, us. So let's end that turn. And there we go. There's our final hand. The dealer's final hand was a 7 of clubs, a 3 of diamonds, and a queen of hearts. They went bust. We have indeed won. And so we can, again, if we wanted to, take another turn. This is turn number 1 of this round. Our hand is a jack of spades and a 2 of hearts. Should we take a hit? Yes. Okay. We take a hit. Ah, we lost. That's too bad. We pulled that 10 of spades out. What a chance. We get 22. That's pretty good. So we can keep up here playing blackjack all day if we wanted to. And we could sit here and if you want to, take this code and you can feel free to add splitting. If you're a big blackjack fan, you can add splitting. You can add other fun little, play around with what it's telling us back here. We currently, it doesn't ever tell us anything except the dealer takes a hit. Depending on the version of blackjack you're playing, sometimes you get to see one card that the dealer has, and you could try printing that out. So there's a lot of fun that you guys can all have, hopefully, with this repo. So any questions on Clojure here at the, I think we're running out of time. Yes, we are. Any questions on Clojure? T/syntax, yes. We can look at it. It has it in the core. So here we are actually requiring different files, and we can, instead of requiring them, we can actually define what we require them as. So instead of just turn, we can actually just say we want it just to be T, so it's nice and short for us. Or you can actually require it and then actually pull it and actually have to do the full namespace for it. That would be the other option. Generally an as, I don't know that you necessarily want to go down to one letter always, but it's a nice little way to keep that nice and clean. Yeah. So the first question is what problems does Clojure really excel at? And a lot of that is anytime you're working with data that's being transformed. So it does it's really nice and efficient at data transformations and consuming large quantities of data. And if you need to, even handling that in a parallel manner. It has some very nice asynchronous methods built in. It's also very nice just for general purpose development. Once you kind of get used to the parentheses, you're like, I want more parentheses in my life. Your second question was, how does it work? How does the Clojure script side of Clojure work? And so it actually compiles all the way down to JavaScript. And you can use it then, you can use that as if you'd use any other JavaScript file. It doesn't really integrate much with like ES 2016 or anything like that as an ES module. But you do have open to you a lot of other integrations. It works. There's some really nice React setups inside of Clojure. You can also go all the way down. We didn't go into it any of this, but you can actually also do interops. So if you actually need to call something in Java or call something in JavaScript, you actually have access to the underlying system if you need it. And they also have ways to build out, if you're trying to build out a library that somebody's going to use, you can actually build it such that even if you have to get down to the JavaScript level or the Java level, you can actually split out stuff so that you can have one library that is usable on either system, which is really nice. So the question was could you build just one part of your application in Clojure script and then access it from other stuff? I don't think I've ever really seen that happening. This man right here may do some more of that. Yeah, it's pretty good. Yeah, so in some of the cases, there's actual like methods or libraries that will give you access to those behind the scenes. And some of them you're actually having to call the JavaScript underneath of it. And so you're wrapping those things if you need to. It depends on which pieces and parts you're needing access to. Alrighty, thank you all very much. Have a great day.
Thank you, Will. Thank you. Come back next week for River's talk. Building a small universe, kind of fortuitous of the space dice. That was nice. Nice little, yeah, space dice. Nice little dovetail in the next